Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on aside as we jump into section 6.5 in the Big Ideas Math Integrated Math 1 textbook. We are now doing geometric sequences. Now, we did arithmetic sequences in the past, and this should ring a bell very familiarly to it. However, this is more on things involving exponential functions or exponents, variable in the exponent, as opposed to the linear ones. So hopefully we start to make sense of it, connecting what we've done with exponential functions and what we've done with arithmetic sequences in the past and how those tied to linear functions. I'm sure we're going to do some things where if they follow what we did with arithmetic, we got to plot some things on some graphs, so get ready for some graph paper usage. Obviously with word problems and exponents, we might have to use the calculator, so get all those tools ready. Jump to the description section down below if you'd like to find the PDF of the problem set, as well as, well, the textbook pages, as well as the any graph paper or anything else that I'll provide for you guys, and find timestamps for things, because I'm going to begin with the lecture portion, and then we'll go on to there. 54 questions for this section. Without further ado, I'll go ahead and get started. You're going to learn to identify geometric sequences, extend and graph them. By extension, I think they mean write the next few terms in the sequence after we understand how a geometric sequence works, and write geometric sequences as functions. This is where we start to do that explicit rule thing, so having that formula in mind. It should look a lot like the other formulas we had, or a lot like the arithmetic sequence rule, kind of how we went about that. So we'll make use of that once we get there. I wanted to say something, I forget what it was. Oh, I remember. This doesn't necessarily have to do with geometry. I mean, it does in its own way, but there's nothing geometry-based that you'll have to know for this phrase here. So there are two different sequences you've now heard: arithmetic sequence and now geometric sequence. Arithmetic sequences feature a common difference. Geometric sequences feature a common ratio. Did I speak too soon? Here we go. In a geometric sequence, the ratio between each pair of consecutive terms is the same. The ratio is called the common ratio. Each term is found by multiplying, not dividing, multiplying the previous term by the common ratio. Like this one here, remember these are sequences, numbers separated by commas, and there are no values in between. We wouldn't connect the dots on a graph, things like that. But you multiply by 5 from one term to the next. Now, we did things with common ratios, or we might have called them common multipliers, to identify whether a function was exponential or not. So that part shouldn't be new. It's just a new phrasing and a new thing that we're doing right here specifically. But this one is a common ratio of 5, so this one's a geometric sequence. Now, identifying, take a look at this. We're determining not just whether it's geometric, but arithmetic, geometric, or neither. So arithmetic can come back here. So for part A, 120 to 60 to 30 to 15, someone might yell, dividing by 2. And it's not that they're not dividing by 2, but we state what they're multiplying by. If they're dividing by something over and over, it is geometric, but we want to state what it's multiplying by. What's that common ratio? So dividing by 2 is also multiplying by 1/2. If you're not sure how to do that, take one term, divide by the one before it. 60 divided by 120 reduces to 1/2. 30 over 60 reduces to 1/2. 15 over 30 reduces to 1/2. Ratios are the same. Common ratio of 1/2 means geometric sequence. Now, we know 2 times 3 is 6, and 6 times 3 sure ain't 11, and vice versa, et cetera, et cetera. So this is clearly not a geometric sequence, but is arithmetic. 2 plus 4 is 6, 6 plus 5 is 11, 11 plus 6 is 17. We understand there's some sort of sequence with adding one more than the one before it. That doesn't make it arithmetic, though. Arithmetic would need a common difference. This doesn't have that. They test the geometric sequence thing by dividing a term by the one before it, showing that they're not the same. And you subtract a term by the one before it, it shows that those aren't the same, plus 4 plus 5 plus 6. So it's neither geometric nor arithmetic, but those are the tests you can do if you have to go that exhaustive. If we know what we're multiplying by, make it easy. If you know what we're adding or subtracting, whatever, make it easy. But that one was neither in that case. Extending and graphing geometric sequences. Well, extending means nothing more, I believe, than just filling out the rest of the sequence, whether it's written as a list or in a table. Here they say write the next 3 terms of the sequence here, 3, 6, 12, and 24. It is a list. They made it into a table. They show the common ratio is times 2. They note that it's geometric, so it will have a common ratio. So we're multiplying by 2. 24 times 2 is 48, times 2 is 96, times 2 is 192, etc. like that. I'll probably just write them as a list straight up right here. And then 64, negative 16, 4, and negative 1. Oh yeah, geometric sequences can have negative common ratios. You know how exponential functions can't have a negative b value, or 1 or 0? This shouldn't be able to have 0. I don't think it'll have 1, but it can have negative 1. It can have negative common ratios. So this one has exactly that. Whenever the signs alternate like this, it's because you're multiplying by a negative. Positive times negative is negative, negative times negative is positive, and so on and so forth. Now the numbers are shrinking, so you're multiplying by a fraction. It looks like dividing by -4, that means multiplying by -1/4. But we still have to write the next three terms in the sequence. So if we're multiplying by -1/4 each time, let's stick in fraction form, shall we? -1 times -1/4 is +1/4. 1/4 times -1/4, so the signs change, right? Positive, negative, positive. 1/4 times 1/4 is 1/16. 1/16 times 1/4 is 1/64. You can see basically it just becomes the fraction version of what these numbers were right here, right? That's the sequence. Or those are the next three terms in it, and you can see again the alternating signs. So when you see alternating signs, it can't be arithmetic. It might be geometric. It's probably a negative common ratio in that case. Graphing a geometric sequence, if you remember graphing an arithmetic sequence, remember this is the first term. I mean, listen, they do that in the table right here, but this is the first term, the second term, third, fourth, fifth, etc. So we're plotting those points. We're not connecting those dots. They say, what do you notice? I don't know. I mean, it looks like an exponential function. That's what I would say for what I notice. I don't connect the dots per se, but it has that curve to it. So, oh, wait, this is an example. Let's see. The points appear to lie in an exponential curve. So they notice the same thing. If they're going to ask that each time, I don't know how to state it differently. Geometric sequences are like exponential functions, right? So they appear to lie on an exponential curve there. Okay. Writing geometric sequences as functions, finding that explicit rule, if you will. If you remember any of these things here, like a sub 1, that's the value of the first term. To find the term a sub n, we're going to take our a sub 1 and do something with it. So let's say that you had a first term of 1 and a common ratio of 5. Notice what happens here, and this is a perfect analogy for how this thing works, or showing you how the rule works here. The first term is simply just 1. You don't multiply by 5 at all. You multiply by 5 0 times. That doesn't mean times 0, it just means you don't multiply by 5. For the second term, you take your first term 1 and multiply by 5, but just once. You just multiply by it once, like to the first power, even, if you will. The third term, you start from that 1, you multiply by 5, 2 times, right? Times 5 times 5. So 5 squared. And 5 cubed for the fourth term, 5 to the fourth for the fifth term, 5 to the 99th for the 100th term. You're multiplying you're multiplying 1 less 5 than the term you're looking for because we start from the first term, right? The second term being 1 times 5, third term is 1 times 5 times 5, fourth term 1 times 5 times 5 times 5, etc. You're multiplying by 1 less 5 than the term you're looking for because this is the first term, then the second term, third term, fourth term, etc. So the nth term, a sub n, is taking your first term and multiplying it by the common ratio n minus 1 times. But we don't use parentheses to write that n minus 1 in here. It's just raised to the n minus 1 power. That's what exponents are. They explain how many times you multiply something to itself. So if you remember the, I want to see if they wrote it. They didn't. But if you remember the arithmetic sequence rule, it looks like this. You add d n minus 1 times like that. Maybe that rings a bell. Hopefully it's something that you remember from back when. Geometric sequences have a very similar thing. Only instead of adding a common ratio n minus 1 times, adding a common difference n minus 1 times, you're multiplying a common ratio n minus 1 times. And that's the explicit rule we can write for ourselves. So there's your formula. Let's put her to use. Write an equation for the nth term of the geometric sequence 2, 12, 72, 432, etc. Then find a sub 10. Now, of course, they want you to use the formula. So we identify the first term, a sub 1, that's our 2. Your common ratio, we're multiplying by 6. You can probably tell from that one, but there furthermore. So you have a first term of 2 and common ratio of 6. A sub n equals 2 times 6 to the n minus 1 power. That's the answer. That's the rule. That's the function. Now, you don't do 2 times 6. Order of operations means do the exponent before multiplication. Just keep that in mind. We are, however, substituting 10 in for n. So 2 times 6 to the 10 minus 1 power. Now, personally, when I do these over time, you're just going to see me turn 10 minus 1 into 9. It's better to avoid making a mistake. Something you can do in the calculator by accident is just raise it to the 10th power and then just do minus 1 after the fact as opposed to 10 minus 1. Do easy calculations when you know how to do them, right? So just raise it to the 9th power instead. Just make it easier for yourself. Anyway, there's that answer. And that's the thing, guys. These numbers are going to get big. So they're probably not going to say the 100th term on these things. They'll either get way too big or in common ratios that are, less than 1, they'll get way too small. So they're going to stick something probably up to maybe term 12. They probably can't get much bigger than that as an overall without getting way too massive. Okay. Oh, hold on. What did it say after that? The 10th term. Oh, that was just the answer. Okay. You can rewrite the equation for a function and use, you can use function notation. It is weird, again, and interesting to me that they don't use function notation for the second guy. I would have probably preferred looking at, if you're going to use function notation here, guys, use function notation here as well. It is really curious. It's not a typo. They clearly intentionally do that. I'm curious as to why they do that specifically with that. But yeah, you can use function notation in place of it. Value of the nth term, you take the first term times the common ratio, n minus 1 times. They do state that the domain of the function is a set of positive integers. Once again, you are only using terms 1, 2, 3, 4, etc. You're not using terms 0, negative terms, or decimal fractional term positions. Let's take a word problem and see what they have to say. Clicking the zoom out button on a mapping website doubles the side length of the square map. Yeah, I believe that. After how many clicks on the zoom out button is the side length of the map 640 miles, given that it begins at 5 miles, is how they're saying it. 1 zoom out click, 5, etc. So understanding this function, we have to come up with a rule that kind of states based on the number of clicks n, we can come up with the side length of 640, the a sub n, but we have to find out for what n that works. Maybe it's the 7th one, something like that. That's what we're working on. Actually, it might be the 7th one. Okay, so anyway, we come up with this formula here. If 5 is the value of the first term, the number of clicks, and 2 is the common ratio because it doubles each time, that's our setup for this thing. They did use function notation on this. It's whatever, a sub n or f of n. But now we're going to set 640 on this side equal to that. And this is where we're going to have to do a little bit more of what we just did in the last section on solving exponential equations. Because that's what this is, guys. It is an exponential equation. We now have to solve for n. So the first thing you would do is divide. Oh, they're using a graphing calculator. I would probably personally, unless it's, it's an integer. You could use this, you could do it algebraically, do they? They do it right here, perfect. Let's look at the algebraic version of it. If you divide both sides by 5, then this becomes 128, and then you can rewrite that as 2 to the 7th power. Remember, your goal is to do matching bases. Now that you have matching bases, you can set these equal to each other and add 1 to both sides. You raise 2 to the 7th power times 5, but the term is 8, right? You multiply by 2 one less time than the term you're looking for. So it takes 8 clicks. 8 clicks total. Because the first click is 5. There. Now you can use a graphing calculator to graph those two parts and you can see where they intersect. They intersect at x equals 8. Remember, x is your n in that case. Okay, that's the end of the lecture portion. Let's go and move into the vocabulary and core concept check. So number 1 says compare the two sequences here. What's the question? Oh, the question is just compare them. I thought they were going to say something about them. So I'm noticing that the first one appears to be an arithmetic sequence. It has a common difference of 2. Arithmetic sequence. D is 2. Whereas the other one here is a geometric sequence with a common ratio of 2. They both start with they both have a first term of 2. R equals 2. They both have a first term of 2, but then the thing changes afterward, right? This is adding 2 each time. This is multiplying by 2 each time. That's the difference between the two. This is a geometric sequence section, by the way, after all. Critical thinking, number 2, says, why do the points of a geometric sequence lie on an exponential curve only when the common ratio is positive? Well, that's an interesting question because, guys, we have not done... exponential functions do not have negative b values. Right? Imagine if it did have a negative b value. Let's use the same idea with this 2, right? But we have a common ratio of negative 2. 2, negative 4, 6, negative... 2, negative 4, 8, negative 16, 32, etc. Imagine what that graph would look like. When n is 1, it's at 2. Boom. When n is 2, it's at negative 4. Boom. And then positive 8. Boom. And then negative 16. Boom, and 32, boom. You're imagining like, oh yeah, the thing would look like this if you could draw a curve. I mean, ideally you can't draw a curve through this, and we don't for sequences anyway, but you can tell that this does not lie on an exponential curve when these things change sign. So when the common ratio is negative, because when the common ratio is negative, the signs alternate of each term alternate, which is not exponential. That's not an exponential curve. They don't do that. They don't do that. And that's the basic thing that we're just going to state right there. You might say, well, how come why don't you, in an exponential function, just make it negative, and then you make the curve do this? That's not what happens with these curves, though. There's nothing you can raise to a power to make 0. There are some things that you can't raise negative powers to. I'll give you a hint. They have to do with taking square roots of negatives, which you can't do. So a lot of things like that are just involved in such a way that it's just not going to work that way. You can try it on a graphing calculator, and it's just going to kind of not really tell you much of anything. All right, guys, I'm going to go ahead and get started with the problem set here. And it is numbers 3 to 54. So let's go ahead and get that ready. Hopefully, I'm not saying it's going to be fast, but hopefully our connection with what we did on arithmetic sequences back when, in tandem with what we've done so far and just the book and just, exponential functions, that these can go relatively breezy now that we've gotten a better handle of all those things. And I'm going to treat these problems as such. Not that this is its own section, but it's a tie-in to everything that we did before, even with arithmetic sequences. Now, exercises 3 through 8 say find the common ratio of the geometric sequence. That means we know that they are actually geometric. So we have to find out what we're multiplying by from one term to the next. Remember, whatever one of them multiplies by, the rest must be as well. 4 times 3 is 12, therefore your common ratio here is 3. Do I have to check the rest? Not really. They do tell you it's geometric. We're not testing whether or not it is, and that's the easiest multiplication that I know I can do without making a mistake on it. So for the sake of that problem, guys, I'm just going to say the common ratio is 3. You can check the rest, but it should be good. Now this one's a little bit different because the numbers are going down. You might state something like divide by 6, but keep in mind we are not stating what we're dividing by, we're stating what we're multiplying by. 6 times what is 1? Well, it's 1/6. And if you weren't sure about that, you can always do 1 times some ratio is 6. 6 times some ratio is 1. And then divide both sides by 6 to figure that out. That's exactly what we're doing. Take one term, divide by the one before it. Heck, 1/6 over 1 is 1/6. That gives you that as well. That's your common ratio, 1/6. Remember, it's what you're multiplying by, not what you're dividing by. Not what you're dividing by. Number 5. Well, these numbers get a little weird, but again, find one that works for you. If you can tell, though, the signs do alternate, which means that oscillating pattern will have a negative common ratio. Only when you multiply by a negative do signs change like this each and every time. 3/8 times what is negative 3? That might take you a second. So maybe go from negative 3 to 24. 3 times 24 is 8. So these signs are changing with the, multiply. The signs are changing each time. So you multiply by a negative. R is negative 8. Yeah, so always work toward that strategy if you can. Number 6 is the same kind of thing. Maybe you don't know 0.1 times what is 1. Or maybe you do. But in this case here, you can also go from 1 to 10 pretty easily, even 10 to 100 pretty easily. That's a common ratio of 10. It's getting bigger, multiplying by 10 on number 6. Number 7 is going down. This one is a little less easy, even from the easiest of numbers to look at, and I don't know which ones are easiest. Sometimes the smallest ones are easiest, which means let's just take the smallest 2 that we have right here. 72 times what number is 54? You would take 54 divided by 72 to figure that out. Now, this is a fraction reduction thing, right? Don't go to the calculator really right now. I'm telling you this is probably a repeated decimal. So for this one, actually, this one's not a repeated decimal. I take it back. But let's just go and do fraction reduction. Maybe you're like, I don't know what these, well, I can divide them by 9. Maybe you know they divide by 9. And then you get 6 over 8. And 6 over 8, you divide by 2. You divide by 2, and you get 3/4. 3/4 is the common ratio here. The decimal equivalent is 0.75. I'm going to stick with 3/4. And it should be a number less than 1. These numbers are getting smaller after all. So a number less than 1, when you multiply by it, will give you exactly that. This one has the same kind of thing here. The signs do change, and that's a way to remind you that, yes, this will be a negative common ratio. Let's go to the smallest numbers to make this easiest for us. Our common ratio is the same as taking 6 over negative 18, but reducing that fraction by dividing top and bottom by 6. You get negative 1/3. Negative 1/3. And this is one where you do not want to put the decimal. That would be like negative 0.3, 0.33, 0.3 repeating. You don't want to do that. Leave it as a fraction. All good. All right, 9 to 14 will determine whether they are geometric or possibly arithmetic or possibly neither. So maybe we'll get 2 of each. Who knows? They might want to get you to test each and every one. So now we don't know if they're geometric. If arithmetic calls out to you like you just know that it is, don't bother testing geometric. For instance, this one couldn't be geometric straight up because, couple reasons. This is not even just looking at the numbers really, But number 1 is the 0. I can't take 0 times something and ever be anything other than 0, so it's impossible there. And number 2, just based on sign, you can't go from negative to positive and then stay positive afterward in a geometric sequence. Arithmetic sequences can do it though, and it looks like to us this is indeed arithmetic. If you can't tell, we do have a common difference of 8. That's my explanation as to how I know that. It says explain your reasoning. It is a common difference of 8. We're adding 8 each time. Number 10 is an interesting thing going on that kind of reminds you of something that a geometric sequence could do, but something that an arithmetic sequence would likely have regarding the pattern. When you look at the signs, they keep changing each time. Something only a geometric sequence could do, but an arithmetic sequence couldn't. But is it arithmetic? You're like, oh, 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10. That's great, but the signs aren't all positive or all negative. They're alternating. This is a case of neither. We're adding 5, and then we're subtracting 11, and then we're adding 17, and then there's a pattern, clearly, and we could even tell the next one would be negative 13 without a real calculation, but there's nothing there. This is a neither case here. Now, Mr. Robinson, you didn't test for geometric. Well, it has the arithmetic flow of 1, 4, 7, 10, 13, like it's adding 3, and a geometric sequence wouldn't do that, but if you want to try it, we'd be multiplying by negative 4 here, and 4 times negative 4 ain't negative 7, so it's not geometric, that's for sure. Number 11. This is once again one of those cases where, you could test for geometric, and it's something that I should really be testing on as a whole. But as we just talked about arithmetic versus geometric, notice here we have, on the arithmetic case, plus 5, plus 6, plus 7. And I can tell you guys straight up that obviously this is an arithmetic, but geometric wouldn't do this either. 9 times something is 14. 14 times something is 20, and etc. There is something you can multiply by, but it's not going to be the same number if you see an addition of one number more than the one before it here. This is just another pattern. It's something, but it's neither arithmetic nor geometric. And that might be the last of the neithers that we have here. We have to run into a geometric here at some point. I'm sure we will. Number 12. Let's see. Number 12. Oh, yeah. Number 12 has something. And you know what? This should ring very familiar to what we did with linear versus exponential. I probably said a lot of the same kinds of things on tests for those here. This has the earmarks of what would be geometric. It goes from fractions to non-fractions, and its growth in such a way. We do times 7 here. Is this times 7? Absolutely. 3/7 times 7, the 7's cancel. When you multiply by 7 here, notice the 49 gets 7 times smaller, but that's okay because that's what the denominator is getting 7 times smaller. That's what's working out. And it's hard to test these fractions through division if you don't really know what you're doing. But 3/7 divided by 3/49 is the same thing as 3/7 times 49 over 3. The 3's, cancel, and 49 over 7 is 7. So yeah, there's a common ratio of 7. This makes this geometric with a common ratio of 7. Now I'll state the neither cases. I didn't show very much work, but a neither case is a way of, it's neither when it's neither arithmetic nor geometric. So if you can show that it's not either or discuss it in such a way, I think it'd be good. Number 13. Again, when I look at this thing, I don't see something arithmetic. The numbers went hugely down, minus more than 100 here, but then they never went negative after. In fact, they go pretty quick to fraction form here, which is looking like something that geometric would do. Now, 24 divided by 3 is 8, and 3 divided by 8 is indeed 3/8. And you might say, Mr. Robinson, I thought you said you don't do division. Well, you don't state division for the ratio. That doesn't mean that dividing the same number over and over doesn't make it geometric. So is 192 divided by 8 24? Yes. So being divided by 8, that also means multiplied by 1/8. Right? If you can say dividing by 8, same as 1/8, things like that, that's all good. 3 over 24 is 1 over 8. Number 14. Signs stay the same. Now, that doesn't mean it has to be arithmetic, right? The signs stayed the same here. You can have all negatives in a geometric sequence. Make sure you know that. You're just multiplying by a positive if so. But this one seems to have a constant increase. We're adding 7 each time. If you're adding 7 each time, that makes it an arithmetic sequence with a common difference of 7. There you go. Okay, let's go. Numbers 15 to 18, we will determine whether the graph represents arithmetic, geometric, or neither, and explain your reasoning. I can just look at the graphs alone and for the most part make some valid. Not necessarily. I thought these would have different patterns. Remember, arithmetic sequences should appear linear. Geometric sequences should appear exponential. Not all curves are exponential, so we do have to maybe look a little bit more at the numbers to be sure. Let's take a look at these ones. It has a bit of an exponential look, but how does it work? It goes from 2 to 10 to 50 to 250. That's a common ratio of 5. So there is a common ratio. It has an exponential curve. So number 15, I'm not going to copy it down, but geometric, R is 5. What I could do, I could copy down the numbers themselves as a list, but I'll just leave it. Number 16. So this goes from 4 to 11 to 16 to 19. 4 plus 7 plus 5 plus 3. It looks like it's adding 7, 5, and 3. It's adding like the next lowest odd number. It'll probably end up subtracting at some point there. Probably then plus 1, then minus 1, then minus 3. I think that's a quadratic. So it's a curve, but it's not linear. It's not a common ratio, but it doesn't have a common ratio here. No common difference or common ratio. Now, like I stated, I believe that's what's called a quadratic sequence. Doesn't matter, but it's not geometric. Number 17 doesn't appear linear as well. We could divide 120 by 2 to get 60. Then you divide by 3 to get 20. Then you divide by 4 to get 5. So you're dividing by one bigger number than the one before it, but because it's not common, it's not geometric. And like I said, not arithmetic. So also a neither case. No common diff or ratio, once again. Try to just copy and paste that. There we go. And number 18, this thing goes from negative to positive and doesn't let up. That's something a geometric sequence just cannot do. This appears linear, though. Going up and right through. Adding 9 plus 9 plus 9. This is an arithmetic sequence with a common ratio, common difference of 9. There we have it. Okay. Now they graphed for us. We'll probably have to, do the graphs ourselves next. So on these problems here, and I know that they made tables for them in the lecture portion. I'm not going to do exactly that. We just got to know how the terms work. They do state that all of these are geometric sequences, so there's not really a big deal in us trying to do an overall test when it comes to the whether it's geometric or not. Come up with what the common ratio is by any two numbers imaginable. For me, I like to say 5 times what is 20. That's pretty easy. That's 4. So if the common ratio is 4, then we have to multiply by 4 from one term to the next recursively to get the next 3 here. 320 times 4 is 1280. 1280 times 4 is, I might have to whip out the calculator for some of these, 5120, I think. And 5,120 times 4 is 20,480. Let's hope those are right. Now, with those involved, they did say graph, and these aren't going to be fun for me to graph in any such way. I'm going to take the first quadrant only, and, we have to do scale change. So I'm copying this. Give me one moment. All right, we're going to do it this way. Work on some scale changes. X's will stay as they are. Well, if they're 4 terms each, right? So let's do let's do 1, 2, 3, and 4 like that. So keep that for all the problems that we do. And then we will look at these scales here. We have to go to 20,000 up here. 20,000, and this is 10,000, etc. So in between is 5,000, things like that. Now that sucks because 5,120, somewhere like right there, right? It's just basically 5,000 pretty much. This is 6,000 right here. So this is the point 3, 5,120. Oh, not 3. Oh, I'm sorry. Hold on a second. We have to go 7 terms deep. Shoot, I forgot about that. It's not just the first 4 terms. So let's keep those the same. Okay, 3, 4, 1, 2, 3, 4, 5, 6, 7. Maybe I should have used a table. Here's 6, 5,120. There we go. 7 goes all the way up to the 20,000 mark and then some. 480, probably about halfway to the next one. So this is where it really takes off fast right there. All the other ones, guys, they're going to be so small. That's why I'm saying the scale is just not going to be great. I don't know why we necessarily got to do the graphs with these, but hey. 2,000, 4,000. So 1,000, 1280 is probably... So this is term 5. We have to do this a few times too, by the way, guys. 320 and 80 and 20 and 5, right? These are going to be very small. 5, 1 comma 5, 220, 380, and 4, 320. Okay, so there's the graph. Best I could do given that graph. Okay, let's move on. Number 20. Okay, this time we're multiplying by negatives. Negative 4 is multiplying each time here, so we have to do 192 times negative 4, etc. I'm going to go to the calculator for these ones. It's not for the first multiplication, it's the ones after, but I don't want to mess up anything after that. So I'm putting times 4 times 4 times 4 in my calculator right now, just like this. Boom, boom, boom. Keep in mind that I have to change signs each time, but these are the numbers I'm otherwise going to write down. So in changing signs, we were just positive. Now we're going to be negative, and then positive, and then negative. Maybe that's the way to go about that, not make the mistake. So negative 768, positive 3,072, and then negative 12,288. So like that, and, you know, graphing again. And I do know we have to go 7 terms this time. Like that. So, oh, they're going negatives. Shoot, I need to get 2 sets of quad. Okay. You win. You know what? I'm going to take the tall graph paper here. I know you're probably downloading my PDFs for these things, printing them out. Maybe, maybe not. But what should I do? What should I do? What should I do? I already started with the small ones. I got to stick with the small ones. I can't get you to have to switch back and forth. Now for the negative 12, I mean, we'll do what we do, right? So this will be 500 and 5,000. Oh my goodness. And 10,000. And negative 5,000, etc. Yeah, these ones start very small here at negative 3. I mean, you can't distinguish between anything else there. And it's the same thing with 12. I mean, these are going so barely up and down here. It's just not really going to be noticeable at all. You can only just pretend right there. Negative 768, this is negative 1,000. So negative 768 goes lower. Clearly, I was going even too extreme with those ones already. But then 3,072. Okay. All right. 3,072. And then negative 12,000 right here. It just shoots down kind of low here. Negative 12,000 like that. So I'm not going to identify the points. You can see what they are. Boom, 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 boom. But there's that oscillating pattern thing. It gets 4 times bigger each time and changes direction. Okay. Number 21. See, that's where geometric sequences get a little tough compared to arithmetic. There's a lot. Numbers get really big or really small really quickly. Number 21 has change in sign as well. Given that it has change in sign, we can find the next 3 terms by following what pattern's going on. If you want to call it dividing by 3, that's up to you. I'd prefer the idea of 1/3, well, negative 1/3 here once we hit fraction realm. But first, if you want to start by saying divide by negative 3, go ahead. Negative 3 divided by negative 3 is positive 1. Then divide by negative 3, it's negative 1/3. But how do you divide negative 1/3 by negative 3? That's where it might be easier to say times negative 1/3. Negative times negative is positive. 1/3 times 1/3 is 1/9. So positive 1/9. So let's still graph that from what we do know and have. 81. Let's go by tens on these. So I'll make this 50. 100. So 81 is... Excuse me. It's first term right here. And then negative 27. Positive 9. Negative 3. 1. Negative 1/3 and 1/9. approaching the asymptote, but from top and bottom is how those guys are working there. Number 22. And that was one of the less extreme ones, right? Number 22 stays negative. All these 5 numbers, and then a -3. So what's happening from one number to the next here? Maybe it's hard to tell early on, but later on you can tell. Dividing by 5. -15 divided by 5 is -3, right? That's also times 1/5. So what's -3 times 1/5? -3/5. What's that times 1/5? The -3 stays on top. This won't change the rest of the way. Just multiply the bottom, 25. -3 25ths, -3 over 125 comes next there. That's the next 3 terms in the sequence. Getting really close to 0, like an exponential function would. This has that going for it. I'll just keep the quadrants like this. Now, -375. Oh, this is going to be tough to kind of bring up here. Even if I call that 500, that's still pushing it. 375 is 75 times 5. So we could go by 75s here. We could say -75, -150, -225, -300, and -375. Then we can clearly see where this thing shrinks as a result of all those. So the first point right here is like that. Then -75 is like that. Perfect. -15 is 1/5 of that. Maybe right there. -3, look, it just gets too close to be able to tell anything right there. Just gets way too small, really close to 0. It kind of looks like 0 at that point. Wonder why they want us to graph it. I wonder if they want us to graph the last 3 terms on these because they just get so big or so small. Number 23, speaking of getting small, 32, 8, 2, 1/2. And then the next 3. Already in fraction realm. Which one's the easiest to work off of to figure out your common ratio? Maybe 8 to 2. We're dividing by 4. That's also times 1/4. So 1/2 times 1/4 is 1/8. 1/8 times 1... Hold on. 1/8 times 1/4 is 1 over 32. And 1 over 32 times 1/4 is 1 over 128. Like that. So, like I said, numbers get really small. Even at 1/8 is pretty close to 0. Never mind the other 2 that are a quarter of that size. They stay positive. So, 32, we can go up here to 30. Is that weird? Yeah, it's weird. Let's do this. Let's go up to 40. Like that. Okay. So, 32 is right there. These are going by 4, so 4 times 8. 4 times 2 is 8, right? Dividing this by 4. Dividing this by 4 is a quarter of that at 2. That'd be 2, half of 4. 1/2 is, a quarter of that, and it's so on and so forth. Just gets small. Whatever. Here's 1 over 128. Somehow it's taller than 1 over 32. And there's that exponential curve going down. We're not connecting dots. Lastly, number 24. This one, at least the numbers will probably be better to fit as an overall, but we got to find out what those numbers are. So, geez, what are these? No matter which set you come across, it's going to be a little weird to look at. So, let's begin with, like, 6 over 4, right? 6 over 4 is 3/2, or 1.5. We got to do 6 times 3/2. So, let's kind of look to these. 6 times 3 over 2. 6 over 2 is 3. 3 times 3 is 9. Now we got to do 9 times 3 over 2. This doesn't divide by 2 evenly, so that becomes 27 over 2. Now 27 over 2 is a mixed number, is 13.5. 27 over 2 times 3/2 is 81 over 4. 81 over 4 is 20.25. So we have to go all the way up to 20 for this, which means I can take these and divide it by 2. Sorry, go by 2s on my scale. So we can go up to 20 here. That would be fitting. And 10. This one, even right here, 16/9, that's still more than 1. Remember, these are going by 2s, though, so 1 is halfway up between these two things. So I have to be a little cautious. 16/9 is 1 and 7/9. Really close to 2. Really close to 2. Probably put about right there. But at least we can fit these points a little better. Now, 8/3 is 2 and 2/3. 2 and 2/3 is not quite 3. It's a little bit under 3, something like that. 4 is exactly this guy right here. So 2 and 2/3, probably a little less, and this one probably a little more. So probably a little like that. So it's not fully linear. There's my 4. 6 is the next one. Very, very slight curve, right? Non-linear, very slight curve. 9 is here. 27 over 2, like I said, is 13 and a half. So here's 12, here's 14. There's 13. 13 and a half is like 3/4 of the way up. And then 81/4 is 20 and 1/4. This is 22, so 1/4. It's barely above 20. It's kind of like that. So you can definitely see that exponential curve going on there. Very slight, and actually probably one of the better ones to plot the points on. You know what I mean? They're harder to calculate and come by, but we did get them. So times 3 halves each time. I liked that graph a lot more than any of the other ones when it came to my scale. All right, numbers 25 to 32. We're going to write an equation and then find a sub 6. Now, I'm noticing that a sub 6 would be just two terms away from here. Probably faster to recursively do like what we did here. Multiply just over twice more to get there. But because we'll have the rule, I'd like to use that rule for these next ones. So number 25 begins it. We have 2, 8, 32, and 128. The 6th term, sure, it's 2 away, but what we have to do in this case here, I'd love for us to establish the value of the first term and the common ratio. The first term is 2, and you're multiplying by 4 each time. So your rule is going to be the first term times the common ratio and minus 1 times, like that. We'll get used to that appearance, okay? So a sub 6 comes from substituting 6 into there, and this is what I suggested in the set here. Turn 6 minus 1 into 5 before you do any calculation, whether it's in your head or on the calculator. So that way you don't accidentally mess up order of operations by typing 6 minus 1 on there when we all know 6 minus 1 is 5. Starting from 2, you multiply by 4 once, twice, 3, 4, 5 times to get to that 6th term. 4 to the 5th is 1,020. No, it's not. Yeah, 1,024 times 2 is 2,048. So the 6th term, 2048. And that looks like that's what we'd probably hit as we move on to that. Okay, number 26. We have 0.6 is the first term. Note that. And also note that it's a decimal in case our 6th term was a decimal. I don't think it will be. So 0.6, negative 3, 15, and negative 75. If y'all notice, we got alternating signs here. The first term is 0.6, but the common ratio times what? I don't know, but negative 3 times negative 5 is positive 15, so negative 5 here. So as far as our rule goes, we'd say a sub n equals 0.6 times negative 5 to the n minus 1 power. Applying the same thing as we did before to find a sub 6, we'll do that for all these problems though. A sub 6 will do 0.5 times negative 5 to the 6th power. Oh, 6 minus 1 power, excuse me, to the 5th power. I think on this one I'd rather go to the calculator for it personally, so I'm going to. So I'll just type that one straight up, okay? 0.6 times negative 5 to the 5th power, right? Go in that format as opposed to like that 6 minus 1 stuff. So negative 1875. Now, I have a question, and they're probably going to ask the question at some point here. I can imagine it's one of the later questions. How would I know whether an alternating sign sequence is positive or negative with one that's very far away? The 6th term is not far away, but let's say I asked for the 100th term. Would I know whether it's positive or negative, and how could I tell? So I don't know if they're going to ask that, but I want to answer some of that now. I expected the 6th term to be negative. I expected it because the even terms here were negative, the 2nd term and the 4th term. So the 6th term should also be negative. The 100th term should also be negative. If they don't ask that question later, I'm glad I covered it now. Number 27. Kind of icky when you see the numbers themselves, and we still have to seek that common ratio. But if you know how it works for the denominators to become half the size that they were before, that means your numbers are doubling. Now, if you weren't sure on that, when it comes to common ratio, our first term is negative 1/8. The common ratio, you can take any term by the one before it. That includes negative 1 divided by negative 1/2, which is negative 1 times negative 2 over 1. Negative times negative is positive. 1 times 2 is 2. You get a common ratio of 2. So we are doubling each time. So your rule is going to be negative 1/8 times 2 to the n minus 1 power. The 6th term. Now, our 6th term should be negative 4 times 2 times 2, right? So negative 1/8 times 2 to the 6 minus 1 power, 5th power. 2 to the 5th is 32. 32 divided by -8 is -4. So we are getting that. Feeling good about that answer, coach. Number 28. Pretend like the decimals weren't there for a sec. You go from 0.1 to 0.9, or like from 1 to 9. Excuse me. Going from 0.1 to 0.9 is the same as going from 1 to 9. You're making it 9 times bigger than it was before. That's true from 0.9 to 8.1. It's like 9 to 81 and 729. We're multiplying by 9 here. But the first term isn't 1. It's 0.1. The common ratio is 9. And there we have it. There's our rule. Let's find the sixth term. This one I wouldn't know off the top of my head, so I'm going to do a fifth term. To the fifth power. I'm going to use the calculator. 9 to the fifth times 0.1. Multiplying by 0.1 is the same as dividing by 10. So this is 5904.9. Still a decimal. Never changing. All right. The first four were lists. Despite the fact that these ones are tables, I can still write them as lists. There's nothing wrong with that. So even though the table's over there, I'm going to still write out the list version. This is still the first term, second term, third and fourth. You guys notice what's happening here? We have the same numbers. I mean, the 0 goes away here because it's a different number. It's 0.0, I guess, here. But the decimal keeps moving 1 over to the left, which means you could just keep moving the decimal over. But mathematically, what are you doing? This is where you're dividing by 10, which also is multiplying by 1/10. Because they're writing these as decimals, I'm fine stating this one as the decimal version if you'd like to as well. So the value of the first term is here. We're dividing by 10, which is multiplying by 1/10, or multiplying by 0.1. So a sub n is 7,640 times 0.1 to the n minus 1 power is the rule. The sixth term will be, and I'm going to kind of cheat just by kind of knowing what we would have to do with these after, but 7640 times 0.1 to the fifth. Now, if I use the calculator, this decimal should go over twice more, so it should be now 0.0764 like that. It will continue to just go another decimal place over each time. So 0.764 would have been the fifth term. 0.0764 is the sixth term. Now, number 30. Here's our first term. Second term, alternating signs, third and fourth. Let's see if we can write the rule straight up from here. Our rule, we take the first term here and multiply it by the common ratio n minus 1 times, right? Now, if you can tell from here to here, we're dividing by -4, which also means multiplying by -1/4. And that's the important part, what we're multiplying by. So all of those follow the same suit. That's what we got. Now, 2 more terms away, using the fraction, here's where, listen, I'm going to stick with the fraction version of this, and I'm actually going to calculate it in my head, even though this one's longer to do this way when they're asking for just the sixth term. To the 6 minus 1 powers to the fifth power. Now, -1/4 to the fifth power, is -1 over 1024. Yeah, I know, kind of weird, right? Then we'd have to reduce this fraction. -192 times -1 is positive 192. So we have to reduce that. What if I told you that these are divisible by 64 and you get 3 over 16? Now, my cheating on that is, I know that 3 times 1/4 is 3/4. 3/4 times 1/4 is 3/16. Now, did I expect a positive or negative answer? For the sixth term, an even number, just like this and this are the even terms here, are positive. I expected this to also be positive. So you will get 3/16. And try and do the fraction version of that if they had well, they didn't have fractions going into that. I take that back. If you did decimal things, I guess we can't be opposed, huh? So I wrote -1/4. If you wrote -0.25, I guess all is good. Numbers 31 and 32 are graphs, but that doesn't mean we can't just write the first 4 terms as they were. First term looks to be 0.5, next term is -3, and then 18, and then -108. Mighty, that shoots up quite fast. Those one where I can clearly see the division is from here to here, or the multiplication. Dividing this by this, you get -6. So the first term being 0.5, common ratio being -6. Here is our rule. The sixth term, I'm going to use the calculator this time. So 0.5 times negative 6 to the fifth power. Now I expect an odd number. So I'm going to get, I'm not going to show it, I'm just writing it out. Negative 6. There's nothing important for me to show you here. Negative 3,888. Okay. And then the final one from this set, the numbers do get smaller. They do call it geometric, so we just got to figure out what the set is here. And I think I already see the pattern. So we start with 224, then 112. Can you tell that that's half of that? And 56 and 28, can you tell those are half? So half of the next term means 1/2 is the common ratio, starting from 224. And yes, I do get, if you did end up just taking half of 28 and half of that number, which is the part I'm probably going to do in my head here. But 224 times 1/2 to the fifth power. 1/2 to the fifth power is 1 over 32. So we're doing 224 divided by 32. And that's, let's see, let's work in our head. It must be 7. Because half of 28 is 14 and half of 14 is 7. So you can check that in the calculator, but we should get 7 for that as the sixth term. Positive 7. Okay. Number 33 on problem solving. A badminton tournament begins with 128 teams. After the first, this looks like a question from the last section, only it's kind of in a different way. After the first round, 64 teams remain. After the second round, 32 teams remain. So we're going to do our sequence based off the number of rounds that have passed. I'm going to make 64 be the first term, because that's after the first round. I want to use it that way. First round, second round, etc. How many teams remain after the third, fourth, and fifth rounds? Well, you're taking half of what you did before. Whether you state divided by 2 or up to you, right? Maybe you didn't need to know anything about this section to answer this question. And I would definitely use recursion here. Take half to get the next, and the next, and the next. So this many teams after round 3, 4, and 5. Those are not fractions that I'm writing. Those are the positions. 16, 8, and 4. Number 34. The graphing calculator screen displays an area of 96 square units. That's the length times width. After you zoom out once, the area is 384 square units. After you zoom out the second time, the area is 1536. What is the screen area after you zoom out 4 times? Now, I don't have to necessarily confirm this, but this looks like it's 12 times 8, and 12 times 8 is 96. We're not trying to figure out the dimensions of these things, but that I do agree, it is 96 in that. So it currently displays 96. After you zoom out once, it's 384. And I'd like to go based off first term here. First zoom out being first term. A second time is 1536. Now, they do not show anything beyond these. I guess we can assume it's geometric from there, and that's where the 96 can be of use. Even though this isn't one of my terms that I'm using, this is after, again, 1 zoom out, 2 zoom outs. So we still need the fourth. So we can zoom out a couple more times this way, or we could come up with a rule. If I did a rule version this time, I would make my first term 384, right? Now, 96 times what is 384? It's not 5. You know what? I don't know what this number is. Let's go to the calculator and see what's going on. We go 384 divided by 96. Oh, it was 4. Okay, I wasn't sure. And 15, it didn't seem like that this one would have been that. So 384. Oh, it's 4. Okay. So your common ratio is 4, and your first term, my first term is 384. That's what I'm going for. So my sequence looks like this. So the fourth zoom out, the fourth term will be the fourth zoom out based on how I set this one up. And that's going to be raised to the third power there. So I'll do 384. This is my calculator. 384 times 4 cubed. And I'm getting 24,576 square units. That is the area. That's based off our window range. Our length times width. We're getting that. Square units like that. Okay. Number 35 and 36. Those are both error analysis. Describe and correct the error in writing the next 3 terms of the geometric sequence. So they're stating it's times -2 each time, which is clearly not the case. We're dividing by -2, so it should be getting smaller as we go along. But you want to really state what you're multiplying by, and it's still not -2. They stated they were multiplying by -2 when they were really dividing by -2, or rather multiplying by -1/2. So let's fix that, as the common ratio is truly -1/2. So we have -8, 4, -2, 1. Signs are changing each time. So 1 times -1/2 is -1/2. -1/2 times -1/2 is +1/4 times -1/2 is -1/8. And yes, I like my fraction version. So number 36, finding the nth term of the sequence. They do have a first term of -2, and they're multiplying by 6 each time. Now they put -6. You don't write negative in that case there. The first term was negative, and all the other terms are negative, and that's only going to be the case if you multiply by positive numbers. Multiplying by a positive number keeps the sign as it is. So they have their common ratio as -6 instead of +6. Now I can see why someone might put that, right? It's very possible that someone sees negatives and like, yeah, multiply by a negative. Negative changes signs. Positives, multiplying by positives keeps things as they were. So this should be a sub n is -2 times +6 to the n minus 1 power. Every time I multiply by another 6, it's just a larger negative. So I'm not finding a very specific term, just the nth term as a generic statement. That's the explicit rule. That's a phrase they don't say in the book, by the way. Not this book, at least. Number 37, modeling with mathematics. The distance in millimeters traveled by a swinging pendulum decreases after each swing. Just a little less each time. A little less each time. So you have your first, second, third terms. Let's write them as a list if that helps us. I don't know. It says, write a function that represents the pendulum swings on its nth swing. They're saying function. I'm hearing more f of n in my head, and I want to go ahead and do that. F of n equals. So we have the first swing at 625 millimeters in distance, then times a common ratio. Now, I can do 400 over 500, and that's 4/5. I'm going to write it as 0.8, though. It's decimal, just because this is a context-based problem. It's likely that if I get an answer later that is a decimal, I'd rather write the decimal than the fraction. So 0.8 to the n minus 1 power, that's in function notation. This is part A. Part B says, after how many swings is the distance 256 millimeters? This is when we got to find which n value gives us 256. So I'm going to set 256 equal to our function on this side. Now, I got to divide both sides by 625 in order to solve for n. This is the same thing that we learned out of the previous section, where we have to actually isolate the exponent term first before we do anything after that. And this is where, again, dividing this, I'll write the well, you know, I said I'll write the decimal version of it. And I don't, hold on, I typed something wrong. And I don't mind writing the decimal version, but it's actually the fraction version that I bet I could answer this question a lot easier than this. I'll show you what I mean in a second. 4096. I got to figure out 0.8 to what power is 0.4096. I'm sure they probably use the graphing calculator on some of these. In fact, they probably do. They probably use the graphing calculator on this thing, and then they solve it. But I want to do this algebraically. I'll use the graphing calculator after if you like. Here's my point. 0.4096 as a fraction. I'm doing this on my calculator. Oh, it's 256 over 625. 256 over 625 on this side. And on this side, I could write 4/5. Here's where this is helpful for me. 4 to the 4th power is 256, and 5 to the 4th power is 625. So this could be 4/5 to the 4th power. And that's a much easier way for me to come up with what that was. So apparently, 0.4096 is 0.8 to the 4th power, something I didn't really know off the top of my head. Now that these bases are the same, I can set these guys equal here, and you'll get n equals 5. Remember, n should never be a non-whole number. It should be 1, 2, 3, 4, 5, 6, 7 in these cases because it is within the sequence that we're answering this thing. So n equals 5. Now, on a graphing calculator, what I probably would have done was set y equal... well, just like you see here, y equals this and y equals that, and find out where they intersect, and you get that. I'll do that for another problem. I already did this one here. Oh, I might do it on this one. Number 38. You've got mail. You start a chain email and send it to 6 friends. I bet you guys don't know what a chain email is. The next day, each of your friends forwards the email to 6 people. The process continues for a few days. So the first email has 6 friends on it, right? After the first chain send. So I'm going to say 6. And every one of them sends it to 6 people. That's another times. This is how many people. Oh, shoot. This is write a function that represents the number of people who have received the email after n days. I don't know if they mean the total number. I feel like they just mean a little more of... I don't think they mean the total number as an overall. As in, if I sent the email to 6 people, now 7 people have it because I did it and those other 6. Like that. I don't think they're doing that. I think it's just something like this. So I start... Let's see. I start a chain email. Let's just make me be the first person still. I'll be the first part of the chain. They're the second part of the chain and the third part of the chain, etc. I'll just have to know what I'm doing with that after. So this is going to be f of n equals 1 times 6 to the n power. We also might just write that as 6 to the n, like that. So let's just do it that way. Part B says, after how many days will 1,296 people have received the email? So I'm the first day, but am I really... See, I said 6 to the n power instead of 6 to the n minus 1 power. So I'm day 0. So day 1 is still the 6 people. I didn't write to the n minus 1. So you could have done this, or you could have done f of n equals 6 times 6 to the n minus 1. That's up to you. This could be the first day of email sending. If you prefer that, that's up to you. One or the other. But part B is now 1,296 people here. So 1,296 equals 6 to the n power. You can do it that way. 1,296 is 6 to the 4th power. So n equals 4. So after 4 days, boom, you got it. And that's kind of how that one's going on there. Okay. Numbers 39 and 40. We're going to write a function that represents the sequence of figures and describe the 10th figure in the sequence. That does sound like stuff we did in the arithmetic sets, but obviously it's a different kind. These are geometric. So number 39, we have this set here. I'm going to copy and paste it. So what's happening is we have a square that's dividing itself into thirds. Each square in the sequence seems to divide itself into thirds. So even when this one goes, thirds, tic-tac-toe, etc., then within here, oh, you could draw tic-tac-toe things within here, right? That's where these ones come up like that. So it just divides itself into thirds from there. So I could say that the number of squares, if we're going by number of squares, they're tripling in each dimension. So they're multiplying by 9. You could say it as a times 9 kind of thing, right? So there's 1 square to begin with. Then there are 9. That's 1, 9, and then I assume 81. So this is going to be, if we use this notation again, this is 1 times 9 to the n minus 1 power, or 9 to the n minus 1 power. So there's our rule. And then describe the 10th figure in the sequence. So I don't know if I have to actually calculate it, but you do a sub 10 equals 9 to the n minus 1 power, or 9 to the 9th power. Now on my calculator, that's going to be pretty big. It's not 81. It's this big number. 387420489. Yes, 387 million squares. 387 million plus squares. Can't really draw that. Yeah, you know what? I'll draw it. It's going to look like this. I bet you know what I'm going to do. It's going to look like this. There you go. That's all them little squares right there. Okay. Number 40. Number 40 is triangles doing the... I mean, listen, it's doing the same kind of thing that number 39 is. It's just triangles instead of squares. I assume they're equilateral. But we take this thing and we divide it into more triangles. Less than we're doing with the squares. We have 1 triangle to start with, and then 4, and then, I'm going to imagine 16, right? Because they're kind of dividing into quarters. This one itself divided into 4s, just like that. So 1, 4, and 16. our rule for this one can be a sub n equals 4 to the n minus 1 power, because we start with a 1. So there's that. And then the 10th term is 4 to the 9th power, 4 to the 10 minus 1. So 4 to the 9th power describes how many triangles there are in this sequence. And there are 262,144 equal or equilateral triangles. Okay. But they're really small now. Number 41. Write a sequence that represents the number of teams that have been eliminated after n rounds of the badminton tournament in exercise 33. What did we? 33. Maybe we didn't. Maybe that was just in the previous. We didn't. So 64 is after one round. Wait. Let's go back to the question. It begins with under 28 teams, but I'm going to let n represent the number of rounds that have gone by, so that's why I wrote 64 to begin with. So let's stick with that. So in writing a sequence there, I am going to have 64 be the first term, just like I kind of had. So number 41. Once again, what we know is like 64, 32, 16, etc. I believe that's how it went, right? And then the sequence now can be, let's go back to an f of n here. I don't think it says part A. But our rule is going to be f of n equals 64 times, and you're taking half. 1/2 to the n minus 1 power, where n represents the number of rounds that have gone by. It says determine whether the sequence is arithmetic, geometric, or neither. This is geometric. Now, I wouldn't have written my rule had I not known what this was, but there's a common ratio of 1/2. Whenever you're knocking the teams down to half of what they were before, this is totally geometric in that way. Number 42 says, write a sequence that represents the perimeter of the graphing calculator screen in exercise 34 after you zoom out n times. Determine whether the sequence is arithmetic, geometric, or neither. Explain your reasoning. 34. The perimeter? So the first, the first one's perimeter, 12, 8, 12, 8. Let's see. So let me just kind of write some things out here. Perimeter of the first one. Now, I forget if I counted it as the first one, but we have 2 times 12 plus 2 times 8, which is 24 plus 16, which is 40. So 40 for the first. Then we had, I'm not there yet. 40 for the first. Excuse me for my yawns. 384, 4 times bigger, but 4 times bigger is doubling each section there. So 384, I think, comes from doubling your perimeter sets. So the perimeter of the second one, 24 times 12 is 384. No, it's not. That's 288. Oh, not 12. 24 times 16. 24 times 16. So 2 times 24 plus 2 times... Right, a sequence represents the perimeter after you zoom out n times. So these ones are... I have to come up with this pattern. So this is 80. Now the question is the next one going to be 120 or 160? The next one had... I think you double what was there. Where is it? 1536. Now 1536 is a result of doing, I think, 48 times 32. 48, I have to do this on my calculator. 48 times 32. So I'm doubling the dimensions of each of my things. Yeah, 1536. So perimeter of the third is 2 48s plus 2 32s, which is 96 plus 64, which is 160. So you can see here the 40, 80, 160, etc. It's here. Now, the first one, I think the 80 was truly after zooming out once. So I don't think the 40 was really a part of it. 40 just helps us understand what we have here. So 80, I think, is actually our first term. 160 is our second term if we use the n minus 1 version of this thing. So our a sub n of this one can be 80 times 2, we're doubling here, to the n minus 1 power, and that can be my rule. You can also do 40 times 2 to the n, like this. We don't often do that 0th term kind of thing, though, for our geometric sequences. Normally, we kind of try and avoid that thing. But there's a common ratio of 2 with that. This is also geometric, with that common ratio in mind. Now, I wasn't sure if it was going to be geometric or arithmetic. I was thinking for a second, maybe this will be 120, but it seems like it's not. Okay, number 43. Writing. Compare the graphs of arithmetic sequences to the graphs of geometric sequences. Well, arithmetic sequences... So, here's how they're the same. Arithmetic and geometric sequences, sequence graphs, are alike in that they are discrete. You do not connect the points. And start at n equals 1. And by the way, the graphs use n, and they use n and a sub n instead of x and y. Right? There's kind of another thing with that. N and a sub n, or f of n, or whatever you want to say. Right? So they are alike in that way, really. But they are different in this other big way. However, arithmetic sequences follow a linear pattern, and geometric sequences follow an exponential pattern. And that's really the big difference between them, right? So that's what I'll say on 43. My back's kind of... Number 44, making an argument. You are given 2 consecutive terms of a sequence. Your friend says the sequence is not geometric. A classmate says it's impossible to know given only 2 terms. Who is correct? Explain. In most cases, 2 terms wouldn't be enough. This specific one reminds me very much of one that I spoke on before as well that stated it couldn't possibly be geometric, and here's why. What I really called out was that 0. 0 cannot appear in a geometric sequence. 0 cannot appear in a geometric sequence. Let's think about why. Mr. Robinson, why not? You have 2 different cases. Consider the following. Case number 1. Not really case number 1, but more reason number 1. You cannot multiply 2 not... Okay, let's start right here. Your common ratio cannot be 0. If it was 0, all your numbers would be 0 after the first term, even if your first term was 0. And case number 2, you cannot multiply out of 0 and get different numbers. And you can't multiply 2 non-zero numbers to get 0. I know I'm not explaining that one best, but basically once I hit 0 in a geometric sequence, every number after would have to be 0, either because I'm multiplying by 0 to begin with, or I'm multiplying from 0 thereafter. And that's just not going to happen. Your geometric sequences will have some sort of pattern. So it's not possible to get -8 as a term based off that and stuff. So who is correct? The classmate is correct. No, I'm sorry, your friend. My friend is correct. Now, in other cases, your friend, the classmate would be correct in stating like, no, yeah, you can't tell from 2 things, because you can't. If I have 2 and 4, who's to say the next one is going to be 6 versus 8 versus 2, right? Or 7. I mean, you need probably 3 terms, maybe sometimes 4 terms to really get that gist of what it is. That's why a lot of the problems do that. All right, number 45 says, is the sequence shown an arithmetic sequence, a geometric sequence? Explain your reasoning. 3, 3, 3, 3. It's actually both. Here's the thing. Arithmetic sequences and geometric sequences, they might resemble that which is exponential and that which is linear. But it's all about, does it have a common difference? Does it have a common ratio? Is it arithmetic? Yes. It has a common difference of 0. Is it geometric? Yes. The common ratio is 1. Multiply by 1 each time and you have that. So as long as it has that, you're good. Okay. Number 46. How do you see it? Without performing any calculations, match each equation with its graph. Explain your reasoning. Well, on number 40, on A, equals 20 times 4/3. Your common ratio is more than 1, therefore you're going to see exponential growth, so that will match with graph B. Of course, they can never match A with A. And then this one here, this has a common ratio that's less than 1, so you're going to have exponential decay, which means that'll match A. So I'll just say exponential growth as R is more than 1. And here R is between 0 and 1. So it's exponential decay. That's how I see it. Number 47. What is the ninth term of the geometric sequence where a sub 3 equals 81 and r equals 3? So you have some options here. And this is one of those ones where I don't know what the best way is to go about it. Yes, you can multiply by 3 each time until you get to 9, and that's kind of one of the options there. You could also kind of come up with a rule based off that. I could do a sub n equals, you don't always have to go off the first term. You could go off this, given that you're going to multiply by 3, n minus something times. N, in this case, n minus 3 times, right? If I want to find the ninth term is 6 away from the third term. So I could write it like this. I don't even have to find the first term here. I could do it like this. And from there, I could multiply by this 9 minus 3 times or 6 times. Right? And just use that. Sorry, this should be a sub 9. A sub 9 is 81 times 3 to the 6th power. So that's basically saying we're at the third term, right? We're going to do times 3 for the fourth term, times 3 for the fifth, times 3 for the sixth, times 3 for the seventh, times 3 for the eighth, times 3 for the ninth. I'm going to multiply by 3 6 times from 81 to get there. So you can do the rule however you need to make sense of it. I could have also come from the first term. I could have said a sub n equals, we could have divided by 3 twice, 27, 9. We could have said 9 times 3 to the n minus 1 power, and you get the same answer if you do a sub 9 equals 9 times 3 to the 8th. A lot of different ways you can do this, but from here or from here, we're going to get the same answer. And I don't know what it is. So I'm going to do 81 times 3 to the 6th. And I'm getting 59,049. 049 like that. I'll just stick with it like that. Number 48, open-ended. Write a sequence that has a pattern but is not arithmetic or geometric. Describe the pattern. We saw a quadratic sequence earlier. I could do the Fibonacci sequence. I don't know if you've seen that before. Just to give you one. Fibonacci sequence is this one right here. Let's see if you can let's see if you can determine what it is that I'm actually doing. I'll leave it right there. Fibonacci sequence takes the two previous, takes two terms, adds them together to get the next one. 1 plus 1 is 2. 1 plus 2... Hold on a second. Let me respond to one text. Give me one moment. Okay, I had a little back and forth text message thing there. I forgot where I left. Well, I know I left off here, and I think I was noting what this sequence was. This is known as a Fibonacci sequence, where you add two terms together and they become the next term. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, like that. Kind of cool. Anyway, it's a real sequence. It's neither arithmetic nor geometric. It is Fibonacci. I mean, look it up. There are a lot of things where this thing appears. It appears in nature. A lot of cool things. I don't even know if Fibonacci knows how many different ways that this thing appears, but it's called the Fibonacci sequence. Magnifico. All right, Fibonacci. Anyway, that's one of them. Neither arithmetic nor geometric. You add the previous term with their current term to get the next term. Okay, number 49, attending to precision. Are the terms of a geometric sequence independent or dependent? Explain your reasoning. Well, if you're going from one term to the next, it depends on the other one, right? So a geometric sequence is dependent. So you take one term, multiply by the common ratio to get the next term. So dependent terms are found, each term is found or calculated, found by multiplying the previous term by a common ratio. I guess that's how I'd answer that one. All right, number 50. Drawing conclusions. A college student makes a deal with her parents to live at home instead of living on campus. She will pay her I talked about this kind of question before. Not this deal kind of thing, but I brought up this question before. I didn't know it would show up here in geometric, but it does. She will pay her parents 1 cent for the first day, 2 cents for the second day, and 4 cents for the third day, and so on. Now, I don't remember what video I brought this up on. If you guys can find that video and comment for me, I'd love to point to what I was bringing up here. Let's see how they talk about it. Write an equation that represents the nth term for the geometric sequence. Now, first of all, the thing here, we start first 1 cent for day 1, and you double your amount each day. So you want to do n minus 1 power still. That way you're multiplying by 2 one less time than before, yada, yada. So that's part A. Part B, what will she pay on the 25th day? I don't know 25th off the top of my head. I know that the 30th day, I don't want to spoil things, but I don't think we're going to do it. So the 30th day, it's like $5 million. So I don't think it's a wise investment for her. I don't think she realized what this would be after some time, how fast this thing grows. So let me try this out. 0.01 times 2 to the 24th power. That is for the 25th day, by the way. So it's $167,772.16. 167. That's just on that day. This isn't a running total. This is, all right, 167,000. Cough it up. The next day, all right, 325,000. Cough it up. Part C. Did the student make a good choice, or should she have chosen to live on campus? Explain. The latter. She should have chosen to live on campus. This might have panned out well for the first 12 to 15 days or so, but doubling over time takes its toll. Remember, after 30 days, and remember, this is just, again, this is on the 25th day. On the 30th day, she would have spent, like, again, $5 million. And that doesn't include the $2.5 million she spent on the 29th day, right? So she should have chosen to live on campus. Man, her parents were like, yeah. So I'm listen, if she has that kind of money, great. Do what you got to do, man. That ain't me. All right, repeated reasoning. A soup kitchen makes 16 gallons of soup. Each day, a quarter of the soup is served, and the rest is saved for the next day. Write the first 5 terms of the sequence of the number of fluid ounces of soup left each day. So by left, it means what's saved, because a quarter of it is served. So if a quarter of it's served, let's say R is 1 minus 1 quarter, which is 3 quarters. So that's our common ratio. And we start with 16 gallons of soup. It says fluid ounces. Are there 16 fluid ounces? No. I have to look this up. I don't know how many fluid ounces are in a gallon. I don't know if this is common knowledge. How many fluid ounces in a... No, not in a cup. In a gallon. 128. I had no idea. And 16 times 128. 16 gal times 128 fluid ounces per gallon. You know what? I might have known something like that. 16.9 fluid ounces in one of those things. Yeah, anyway. I didn't know if it was 120. I didn't know it was 128. So 16 times 128 is 2,048. So they make 16 gallons of soup. So 2,048 fluid ounces. So they make that many, and then each day a quarter of soup is served. Hold on, let me check all my conversion things there first. Okay, just making sure I typed gallons there. All right, so that's there. So each day, a quarter of the soup is served, etc. So after one day, you're going to take 3 quarters of this already. So 2,048 times 3 quarters should be our first term, really. So let's do 2,048 times 3 quarters, and now I have 1,536. So this is the first term. So 1,536. This is write the first 5 terms. 1,536. Let's do that times 3 quarters. I would just do times 0.75 each time. Times 0.75. Sorry, I'm doing this on my calculator here. So I'm going to use decimal answers if they get it. So far, they're not decimals, so do what you got to do. Yeah, none of them are decimals. So 1536, 1152, 864, 648, 486. That's cool. 864, 648, 486. That, I don't know if they realize that those numbers do that. That's really cool. Write an equation that represents the nth term of the sequence. Well, that's part A. I kind of would have preferred to do that first there. Part B is A sub n equals, so 1536 is the first term after 1 day, and 3/4 the n minus 1 power there for n days. Part C, when is the soup all gone? Explained. Theoretically or mathematically, the soup would never be all gone, because if you take 3/4 of what you had before, then, like that. So theoretically, the soup is never gone. Taking 3/4, I mean, this is the same reason for the asymptote things that we have. Taking 3/4 of some amount of soup will be less than before, but never 0. This is why exponential functions have horizontal asymptotes. Now, maybe you start to say, oh, when are you less than 1 fluid ounce or whatever? In real life, eventually there won't be enough to serve. In real life, however, eventually you will have too little to serve after some point. Now, when is that? You have to do it with a number that's more than 0 to find it out. You can set it equal to 1 and figure it out, but you can't do it with 0. Exponentially. Mathematically and exponentially. All right. Just a few more problems here. Number 52, thought-provoking, says find the sum of the terms of the geometric sequence here. Explain your reasoning. Write a different infinite geometric sequence that has the same sum. Okay. I'm trying to decide how to do this without talking about geometric series. I mean, this is a series if you're finding the sum here. Is this an infinite geometric series or finite? Explain your reasoning. Write a different infinite geometric sequence that has the same sum. Best I can do for you is what I know. And what I know is geometric series rules. And the proof of it is way too weird. We did it for arithmetic series. That's not too bad. Geometric series is a lot more provy, which is a little weird. So best I'm going to do is give you an answer based off of, well, here, let's do this. Let's add these to start with. So as far as the sum, it's 1, and then 1 plus 1/2 is 3/2. And then 3/2 plus 1/4. Oh my gosh. This could be a long problem. 3/2 plus 1/4 is 6/4 plus 1/4, which is 7/4. And then 7/4 plus 1/8 is 14/8 plus 1/8, which is 15/8. And you can see how these numbers get, look, it was 1, then 1.5, then 1.75, then 1.875, I believe that is. And you can see how it's getting higher and higher. Now, how high does it get? I believe it gets closer and closer to 2, the way that it's kind of converging like that. You can see that we're always one number less than the thing that makes it 2. So, for example, the next one would be over 16. I bet that would be 31 over 16, right? Because you're adding the 15 to it. And then over 32, I bet it would be 63 over 32. It gets really close to 2 without actually becoming 2. The actual formula for that, the sum of the infinite series, you take the first term and you divide by 1 minus the common ratio, and this common ratio is 1/2. The 1 over 2 and n minus 1, yeah, that's fine. So 1 over 1/2 is 2. So that means we're approaching 2. Approaching 2. I don't know how much I can say about that as an overall for you to understand it fully without me adding those and just showing you how it's getting closer and closer to it. Write a different infinite geometric sequence that has the same sum. Oh dear. Well, I could do it based off my formula. For my formula, I could say, let's take 1/2 and divide it by 1/2 divided by 1/4 would give me 2. So to divide by 1/4, I have to do 1 minus 3/4. So we could do 1/2 times 3/4 to the n minus 1 power. So that would be 1/2. What's 3/4 of 1/2? 3/8. Hey, you can't follow what I'm choosing as a string. 3/8 times 3/4 is 9/32. So these should also add to that. And 27/128. You can't copy mine. Yes, you can. But how I got this is for different reasons that you won't know. It has to do with my formula that I'm using here. I shouldn't have erased what I was putting right there. So yes, that is an answer for another rule that should add closer and closer to 2. That's a tough question for IM1. There's no reason that you guys should understand how to do that one. Number 53, open-ended. Write a geometric sequence in which the second term is less than the first term, which is less than the third term. So a sub 2 being less than a sub 1 being less than a sub 3. I'm thinking about one where we're changing signs. That would work out. This is the smallest as it's negative, and this is smaller than the third. So something like 1 and then -2 and 4, like that. They're changing signs in that way. Common ratio is -2. So this is your second term. This is your first term, and that's your third term, like that. So that would work out that way. They said write a sequence, so this would be one right here, where you're swapping signs like that. Excuse me. The last question, number 54, on number sense, says, write an equation that represents the nth term of each geometric sequence shown. We have a sub n and b sub n. Okay, nice. So a sub n, I have a common ratio of 3 with the first term of 2 that looks like that. And b sub n, I have a first term of 1 and a common ratio of 5 like that. You can also turn it into just 5 to the n minus 1 power. It's up to you. It says, do the terms a sub 1 minus b sub 1, a sub 2 minus b sub 2, etc. form a geometric sequence? If so, how does the common ratio relate to the common ratios of the sequences above? That's going to be part A. So for part A, 2 minus 1 is 1. 5 minus 6 is -1. I don't know the answer to this. 25 minus 18. Oh, wait, hold on. 18 minus 25. 18 minus 25 is -7. It's clearly not geometric. And 54 minus 125 is -71. Wait. Yeah? I think -71. Is it geometric? No. No. So it said, if so, how does the thing relate? No, not geometric with that. Part B, now do a sub 1 over b sub 1. So 2 over 1 is 2. 6 over 5 is, well, it's 6/5. I'm just going to keep it like that, 6/5. 18 over 25 is 18 over 25. There's nothing I can do with these because they can't reduce, right? So they can't reduce, but yeah. So we have a list that's 2, 6 over 5, 18 over 25, 54 over 125. And they're asking here, does this form a geometric sequence? This one does. This one, remember, the 2, by the way, is 2 over 1, right? You're literally just dividing 1 by the one before it. And this makes sense because they were both geometric to begin with. So on top, you're multiplying by 3. On bottom, you're multiplying by 5. That means you're multiplying by 3/5, right? So that totally makes sense that is. So times 3/5 each time, and that's what makes it so. So how does the common ratio relate to the common ratios of the sequences above? You multiply the top by its common ratio and the bottom by its common ratio. It is the quotient of the common ratios. Of each sequence. So the top we were multiplying by 3, the bottom we're multiplying by 5, and it seems to be just that, times 3/5. And that's the answer. That is the answer, and guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We have one more section to go on, I believe, recursively defined sequences. I don't know to which extent they talk about the things. We've done some things on recursion, just not in the formula realm. It might be confusing looking. We'll see what they want to do with it, but I assume they're going to do some arithmetic as well as geometric, so be ready to do both. So guys, thank you so much. Take care. I'm going to see you in the next one.